or not slowly varying. Essentially, these are quickly varying functions. Okay. Then compact schemes can still provide the padded schemes can still provide you with a good solution as compared to other methods such as CDS2 or CDS4, right? Because these cannot provide, these can only provide better answers or correct answers only for slowly varying functions. Okay, that means another way to think about it, as we were discussing yesterday, is that you can take finer meshes. You need to take finer and finer meshes when you want to do it with CDS and CDS2 and CDS4, because you want to essentially reside in this region, right, where it starts deviating. You don't want to use it anymore after that. Whereas if it comes to compact scheme, you can actually go all the way to even little bit coarser meshes because it's still matching. So your H can be still larger, so that you can, even if you have the same wave number that you have to resolve, you can still take H to be larger so that you are still in this region, till this region. Okay, that means even if your mesh is coarser, the compact scheme will give you a better answer even for somewhat quickly varying functions. Of course, the best would be that if you have a function that goes all the way much higher and then drops, those can be constructed with higher order compact schemes and methods such as spectral schemes and so on, which we are not going to go into detail. But the takeaway is that by utilizing by starting off with the proposition that your fj prime not only depends on f values at neighbors, we are also making it depend on neighboring derivative values. That basically has led to this discovery that we can have a scheme that has better accuracy on a compact stencil, and it can give you better accuracy in terms of the wave number space. Okay, so that is the takeaway. Okay, so but only the price you are paying is that to calculate the derivative, you are now solving for a system of equations. That means you have to solve for a TDMA, which was absent in the case of CDS2 or CDS4 in terms of these explicit schemes where you just have to plug in the function value and then get the derivative. But here you can't just plug in the function value. The function values go into the right hand side into this one, but you still need to solve for this TDMA to get all the derivatives at once. Okay. So that is the idea. Okay, any questions so far on this? Is it clear, or any questions that you have immediately?
No, sir. We have to review and then come back.
Okay. All right. Then let's move on to calculation of truncation error. Okay. Calculation of truncation error for essentially now what we want to do is that we want to develop a procedure. We want to develop a procedure in which given a function, that is f, or given a governing equation, let us say, so calculation of truncation error. So, okay, so we want to calculate the truncation error. So we will take one particular governing equation. So the governing equation is, let us say, the transient heat conduction equation. Okay, transient heat conduction equation. I don't know whether you remember the transient heat conduction equation. I can write it as partial T by partial T equals alpha dou square T by dou x square. Transient heat conduction equation in one dimension. Okay, so we are only looking at one dimension as of now. Okay, so that means dou square T by dou x square is there, and then T is the capital T is the temperature. Okay, although I'm going to change this, instead of T, I'm going to use a different variable called U. And alpha is the thermal diffusivity. Okay. Okay, so I'm going to write this as, instead of t, I'm going to use as dou u by dou t equals alpha times dou square u by dou x square. Okay, where little t is the time, x is the spatial coordinate. Okay. Fine, that's what we have. Now, okay, now what does this mean? Okay, now, of course, we can solve for this, but then this is a, this is what kind of an equation is this? Is a partial differential equation, because there are derivatives with respect to time as well as derivatives with respect to space. So as a result, this is a partial differential equation, right? This is not an ordinary differential equation. And then for this equation, we need, of course, initial conditions and then boundary conditions. So how many initial conditions and how many boundary conditions do we need to be able to solve this equation? To solve, we need initial conditions and boundary conditions together with the governing equation. So how many initial conditions and how many boundary conditions we need? Can anybody tell me?
One boundary condition and probably no. So basically, if we have to integrate it twice, necessary, if I'm not wrong, right?
Correct.
So at
So
least
the yeah.
initial condition should be
So-
1 and boundary condition should be 2. In my
Correct.
opinion.
So because there is a derivative with respect to one single derivative with respect to time, we need one initial condition and then two boundary conditions, right? Because this is second derivative. Okay. So we need these things. Okay. That means we need to, somebody has to specify u at t equal to 0. That is the initial condition over the entire domain. Let us say if you take the domain as going from 0 to L, let us say we are trying to solve how does the heat conduction happen in a particular rod, which is maintained at different temperatures. Let us say this is maintained at T0, this is maintained at TL. We want to calculate what is the temperature distribution within this rod as a function of space as well as time. Okay, so we want to specify u at t equal to 0, but then that needs to be specified over the entire length. So this is your initial condition. Okay, similarly, you need to specify boundary conditions. U at x equal to 0, that is at the left end. You need to specify it for all times, that is 0 to capital T or T final. Okay, this is the boundary condition 1. Similarly, you have to specify value at x equals L for the entire time, that is 0 to TF, right? PC2. That means for the entire duration of the time when you are conducting the experiment, you have to specify what is the boundary condition, right? So it means this is the initial condition and then the two boundary conditions. So with these conditions, and this equation can be in principle solved either analytically or numerically. For an equation like this, even analytical solutions exist, but then we are not going to take the analytical solution route because we are going to look at the numerical methods part of it in this course. So this can be solved now numerically. But then if it can be solved, so what is the truncation error that is involved? That means we want to use certain schemes that we have learned, right? We have learned the forward schemes, backward schemes, and so on, central schemes, and so on. So if you want to discretize them with those schemes, using those schemes, we want to discretize this equation, then what is the truncation error we get? And then is my equations consistent, right? When we say consistent, does the truncation error go to 0 as your delta x, delta t are made to go to 0? That means, is it consistent or not? So these two questions we want to understand. So of course, now you can discretize this thing. Now this can be solved in many different ways. This can be discretized using certain methods, okay, or schemes. Okay, we're going to use look at what are the different schemes available to discretize this thing. So discretization means we are going to convert this partial differential equation into an algebraic equation. Okay, or not only just algebraic equation, we are going to convert it into a system of algebraic equations. Okay, that's what we're going to do. We're going to convert this partial differential equation into a system of algebraic equations. Okay, so the first one is known as the Euler's explicit method, okay, or also known as forward time and centered space. Okay, we call it FTCS, forward time centered space, or Euler's explicit method, in which case we're going to discretize this thing as dou u dou t equals alpha Rho square u by dou x. Yeah. Hello. Okay. So we're going to discretize this thing using forward time center space, which is called FTCS. Then we are going to write it like u I n plus 1 minus u I n divided by delta t equals alpha ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square at n, n, and n. Okay. So the idea is now is that if you have the solution at one time level n, you want to advance it to the next time level u n plus 1. Okay, so the superscript here denotes the time level. That means you are moving from nth level to the n plus 1th level. And then the subscripts here, I plus 1, all those things denote the spatial location. Okay, that means it's going to be I plus 1, I minus 1. So you are making use of both of them. So we have now discretized this dou u by dou t, just like the spatial derivative. I have written in terms of at the same grid point, that is ui at both values, but then this is n plus 1 and then this is n. So I have approximated dou u dou t as ui n plus 1 minus ui n divided by delta t. That is the approximation for this time derivative. Alpha remained as it is, and then dou square u by dou x square, I have used the central difference scheme or centered space, that is basically ui plus 1 minus 2 ui plus ui minus 1 by delta x square. This we have already derived, right? We have derived second derivative to second order accuracy, the formula. That the same formula I have applied. Now, what is explicit here, or what is forward time? What is explicit or forward time means the entire right hand side is evaluated at the time level n. That means, as you can see, I have put n here, n here, and n here. Okay, so that means only n plus 1 only comes on the left hand side for ui, nothing else. Okay, so this is called Euler explicit method. If everything on the right hand side is obtained at the known time level, that means we know the solution, the entire solution ui at time level n. This is already known, right? For example, you start from ui of 0. Let us say this is the initial condition. So from the initial condition, you're going to march ahead. Okay, so that is what you're going to get ui at 1. Then with that, I mean, when I say ui, we know ui at all the grid points. Similarly, ui1, from ui1, you are going to get ui2 and so on. Okay, so that is how you're going to march. So if the entire right hand side is evaluated at the nth time level, that means everything is known there. That is known as an explicit method, because you don't have to solve for a system of equations because it is explicit right now, because you just have to substitute for known values of uin, ui plus 1n, uin, ui minus 1n, and then use the values of delta t, delta x square, alpha. Just calculate uin plus 1, right? That means if you have this 1D domain, so you're going to make use of all these values. Let us say these are available at nth time level. So you're going to write this as you are going to calculate what is ui n plus 1 at this point using the existing values. Let us say these are all available at nth level. So these are all u at nth level. Then you want to calculate them at n plus 1th level, right? So that means you're going to calculate this based on what is this is n plus 1th level. Then you're going to make use of ui at n, and then ui plus 1 at n, and then you're going to make use of ui minus 1 at n, and so on, and then calculate this thing. Then you're going to march to the next grid point, right? You're going to march to the next grid point, make use of this, and then calculate, and so on, right? So that is how you can calculate. And this basically requires only a substitution. There is no need for solving for system of equation. You just need to substitute everything on the right hand side and the left hand side and update the value. So that is why this is explicit. This is the easiest way to solve a differential equation, a partial differential equation. Just substitute and then move forward. Of course, there are problems with it and so on, limitations and so on, that we will come to it later. Now, the other method is known as the Euler's implicit method. Okay, which is known as the backward time and centered space, or BTCS. Okay, so this is backward time center space. Again, we have this equation dou u dou t equals alpha dou square u by dou x square. So the left hand side is discretized as before, ui n plus 1 minus ui n divided by delta t equals alpha times. Now the right hand side is evaluated, that is ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square. But then this is evaluated at the time level n plus 1 and plus 1. Okay. Now that means the entire RHS is evaluated at n plus 1 instead of at n. Now this may sound surprising because we don't know the values of ui at n plus 1. How can we evaluate the right hand side? Right? I mean, how can you evaluate right hand side at n plus 1 when we don't know them? But then, as you can recall, what you can do is you can send all these guys to the left hand side. On only this guy will only go to the right hand side. Everything else will stay on the. Everything else will come to left hand side. Then this basically forms a at n plus 1, you have now dependency on ui plus 1 and ui minus 1. So again, just like what we have seen in the case of Faraday schemes, this is going to form a system of equations, right, with this particular term and associated coefficients on the right hand side. So basically, you will end up with solving for a linear system of equations, okay, in order to obtain u at n plus 1 for I, where I goes from 0 to n, okay. Let us say some 0 to n values are there. So now this may sound a little more complicated because earlier in the Euler's explicit method, we were able to simply substitute the values and then calculate, whereas now it doesn't make sense because now we have to solve for a system. That means we have to solve for ax equals b to be able to actually get u at the n plus 1 time level. Now, this seems like it is more computationally expensive than the Euler's explicit method, but nonetheless, there are some certain advantages in terms of stability, where the delta t that you would choose in the Euler's implicit method can be larger than the delta t that you would need, that you must use in the Euler's explicit method. Okay, so there are certain advantages which we will come to that little later, but as of now, this is how these two methods look like. Now, of course, I am saying you end up with a system of linear equations that is subject to the fact that this alpha, which is the thermal diffusivity, is a constant, right? If alpha happens to be a function of temperature, that means in this case, if alpha happens to be a function of u, where you have several fluids and several solids, where the thermal diffusivity is a function of the temperature, right? If that is the case, then this is not going to be these equations are not going to be linear anymore. They're going to be non-linear. That means you need to linearize them before you can solve them, right? Otherwise, you end up with a system of non-linear equations which needs to be calculated. That is more complicated. So we'll try to linearize them and then bring in this non-linearity through other means. Okay. So eventually, you're going to end up with a system of linear equations. Even if the right hand side is not linear, you're going to linearize them and then end up with these equations. Okay, and then somehow bring in this non-linearity later. Okay, so those are the two different methods. Then there is one more prominent popular method that is known as the Crank-Nicolson scheme. Okay, so unlike the Euler explicit method or the implicit method, so what we have seen is that so in the Euler explicit or implicit, we are trying to evaluate the values at either n or at n plus 1 time levels. Okay, whereas in the Crank-Nicolson scheme, the values are evaluated n plus half time level. Okay, that means you have partial u by partial t equals alpha dou square u by dou x square. That means you're going from this is your nth level, this is your n plus 1th level. Then you are evaluating at the n plus half. Okay, n plus half. Okay, if that is the case, then this entire thing is evaluated n plus half time level. Let me write this on the new in the top, n plus half, n plus half. That means, how do I calculate this at n plus half? So you should think of n plus half as being the midpoint of n and n plus 1. That means we are applying some kind of a centered scheme between n and n plus 1 about n plus half, right? That means this is going to be ui n plus 1 minus ui n divided by delta t. Now, this may look like, well, this is the same as the Euler explicit method or implicit method, but it is not, because in the Euler explicit method, you are evaluating it from here using some forward difference, or you are evaluating from here using some backward difference. But then in this case, you are evaluating from this point, you are evaluating in terms of these two. Okay, so this is basically centered about n plus half. That is the difference. But then now the difference will be much more prominent on the right hand side. So on the right hand side, now I have to evaluate this at n plus half, which means I will take this. So because this was derivative dou u by dou t, I could write it as ui n plus 1 minus ui n by delta t. Whereas this one, there is no time derivative, but I want to calculate this value at n plus half. So I'm going to write this as average of dou square u by dou x square at time level n plus dou square u by dou x square at time level n plus 1. Okay, so that is the difference. That means now I'm going to plug in this central difference discrimination for this, and then central scheme for this at the corresponding n and n plus 1 time levels. That means ui n plus 1 minus ui n divided by delta t equals alpha by 2. And what we have is ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square, all evaluated at n, plus you have ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square, all evaluated at n plus 1, n plus 1, n plus 1. Okay, so that is the discretized equation for the Crank-Nicholson scheme as applied to for the solution of one-dimensional heat conduction equation, transient heat conduction equation. Okay, so so we have learned three methods, that is the Euler explicit, Euler implicit, and then the Crank-Nicholson schemes. Okay, so all these we have learned with the application of to the one-dimensional heat conduction equation, that is dou u dou t equals alpha dou square u by dou t square. Okay, this is the one-dimensional transient heat conduction equation. Okay, so that's what we have learned today. Now what we need to do is essentially we need to develop a formal method for the as you may recall, the thing is that now it is kind of very straightforward, or is, to calculate the truncation error for these schemes. For example, for the Euler explicit method or Euler implicit method and so on, when you apply it to one-dimensional heat conduction equation, transient heat conduction. But then, nonetheless, although it is very easy to comment from the equations, we're going to still develop a formal method, because we should be able to tell what is the truncation error given a set of PDEs, or given a PDE and its corresponding algebraic equations. Okay, using that means when you are given a PDE and a particular discretization, we should be able to tell what is the truncation error. So when we are given a partial differential equation and a particular discretization, we should be able to tell what is the truncation error, and we should be able to also comment on whether this particular discretization is consistent or not. Okay, so that we should be able to tell. For that reason, we're going to develop a formal method for the calculation of the truncation error that we will apply, and then see how it can be done, and then comment on whether it is consistent or not. So that is the idea moving forward, which we will take up in tomorrow's class. Okay, if you have any questions, you can ask me. Otherwise, I'm going to stop here, and then we'll catch up with in tomorrow with calculation of truncation error. Any questions, anybody?
Sir, we will study and then we'll come back with questions tomorrow, sir.
Sure, definitely. I look forward for the questions and discussion. Okay. Fine. Okay, then I'll stop here, guys, and talk to you tomorrow at 4 o'clock.
Sir, one request, sir.
Sure.
Basically, sir, for the midterm, probably is
Yeah.
approaching in 2 weeks' time or
Correct.
like so. So, sir,
Yeah.
if you could give us a clarity regarding the syllabus that will be like included for the midsem, that will be helpful for us, sir, because
Sure. Yeah. So we have finished what? We have finished the 2 chapters, huh? So we finished 2 chapters, isn't it? And we are in the 3rd chapter right now, isn't it?
right,
Yes, sir. Yes, sir.
Yeah. So we finished the solution to system of linear equations and solution to system of nonlinear equations, right? First 2 chapters. And then this is the 3rd chapter. I think we can keep the first 2 chapters. That's fine.
Thank you, sir.
This we can keep later for the final exam. Anyway, will contain the entire syllabus. We'll keep the first 2 chapters.
Thank you, sir. Thank you very much.
That should be fine, I think, because this will, we'll probably be just finishing up by the time of the, midterm, probably 1 week before. You may find it too much to be tested. So we will keep, everything else for the entire syllabus for the final exam. But for midterm, we'll keep so midterm chapter 1 and 2, that is solution to system of linear equations, and then solution to system of nonlinear equations, because by then you will also finish this assignment, and then you would not finish the assignment on the 3rd chapter yet. Okay, so that will be the syllabus. Yeah.
Noted, sir. Thanks, sir. We will work.
All right. Okay.
Thank you, sir.
Yeah,
Thank you
sure.
so much.
Thank you.
Okay.
Sir,
Thank you, everyone. Yeah.
Sir, just one request, sir. Sir, actually, our time span, this semester started very late for us compared to the previous one. So the time gap between the midsem and the endsem is only 1 month, sir. We have.
Correct. Yeah.
So considering that, sir, chapters 3, 4, 5 itself will be a bit heavier. So will it be possible we can have only those 3 chapters for the endsem exam, sir? And that chapter.
Usually final exam will have everything together. I think that is for your own benefit. So I think you should not worry. But the one general rule is essentially there will be more assessment from whatever is not tested.
Yes, sir. Actually, we had few subjects where we had the whole syllabus for the endsem, though half or 40% was covered on the midsem. But certain subjects we had that exemption where it was cut off to the midsem, so that only the portions that were covered or the ones that are pending after the midsem was considered for the endsem. Just for this one, sir, because the calculations are pretty voluminous for us, sir, to be honest.
Yeah. No. The thing is, the idea is, as we said before, we'll have the entire syllabus for final exam. Okay, so that is that's going to be there. But what I'm trying to say is that when you learn ODEs or PDEs,
okay, sir.
Okay, these are the 4th and the 5th chapters. Now we are in the 3rd chapter, which is the basics of finite difference method. Now the syllabus is actually backwards.
Okay.
Not backwards. It's not the syllabus. The syllabus is actually forwards, but the application is backwards.
Yes, sir.
Because the solution of ODEs and PDEs using finite difference method will lead to system of linear equations and system of nonlinear equations.
Understood, sir.
So what we are learning is we learned this first, next this one, then we're going to 3, then we're going to 4 and 5. So if we say the syllabus is only 5th chapter, it is not faithful, because to solve it anyway, you need discretization, and then once you have the equations, you have to use SLE to solve it.
Okay, sir. Okay.
So as a result, we cannot do away without 1st and 2nd chapters, something like that.
Okay, sir.
But then anyway, the assessment will be more from, let us say, whatever is not tested already in the midsem. Okay. So, but then anyway, the other way to look at it is, because there is not much time gap between midterm and final exam, all these things are also fresh in your mind. Like, that it is not that you have learned this in 1 month and then after 5 months we are testing it. So,
yes, sir.
If I flip the same argument backwards, so everything is fresh in your mind, and then you can easily score if things are asked from chapter 1 and 2.
Understood, sir. It's clear, sir. Thank you.
Yeah,
sir.
I
Thank
think
you,
this
sir.
kind of reasoning to students only comes from experience. So, yeah. Okay, I think it should be fine. I think we'll see. Yeah.
Professor, just
Thank
one
you.
request that I would request you to be little kind towards us, sir. Actually,
Say it again. Sorry.
little kind towards us, sir.
Yes, sir.
Like
Yeah,
whatever you
yeah.
say,
No problem. No
Yeah.
problem. I think you will be able to solve. Not an issue. We'll see. I mean, anyway, I'll have time to evaluate midterm and then see. I mean, we have to also see the assessment stuff and all. So that is fine.
Sir, will it
Yeah.
follow if we may ask? I mean, the questions might be looking relevant to what was asked in assignment, or
Yes. Yes. Very much. Very much.
Okay, sir.
okay, sir.
Yeah.
Thank you.
There may be some simple changes. See, there may be some simple changes, but then it will be similar to what is asked in the assignment. Okay.
That's fine, sir. Fine, sir.
Yeah.
Thank
It
you,
will be
sir.
on those
Including
lines. only.
the program. I mean, programming.
The programming part is not there as such for testing.
Okay.
It's only the analytical stuff that you're doing hand calculations.
sir.
only. The programming part.
Sorry.
Yeah,
Since
go
you
ahead.
asked that there will be some derivation also asked, like suppose, sir. So which you have derived in the class. So like if you can just populate the list. Okay, among this anything I can ask, that will be very pointed for us actually to prepare in that.
Right, right.
And
No, we'll
then-
make it open notes because you guys are asking. We'll make it open notes. Not a problem. I will check with the team if I can. How that can be allowed. If you can bring in your handwritten class notes, I think they allow that.
Right.
That should be fine. Yeah, yeah. So that should be fine. See, derivations means if you follow what is done in the class, how we are proceeding in a similar way. I don't mean to say there'll be some new derivation for which you have to think a lot and stuff like that. You would basically follow the similar steps. But the derivations are better because those are scoring for you rather than
Yeah.
numbers. Because numbers you may make mistake and everything will become incorrect after that.
Right, sir.
So that is the thing. So, but derivations, if you follow what we're doing, I mean, they will not be too big. See, for example, basics of finite difference method, you will see only derivations, right? But then derivations have some structure. You start from somewhere and then you go in the same order. For example, calculation of truncation, you will see that. So something like that. But it should be fine. I think you should, all of you should perform well in the exams. Not a problem.
Sure, sir.
Once you spend time on the assignments, try to understand. Ask questions to me and the TAs, learn. Then I think you should have no difficulty.
Thank you so much, sir. Thank you so much.
Okay, thank you. Thank you, guys. Yeah.
Thank you, sir. Thank you, Umesh, sir.
Thank you. Talk
Thank
to you
you, sir.
tomorrow. Thank you, guys. Yeah. Bye.